All right, next we're going to look at linearization and differentials. So you know how early on we did several times where we would find the derivative of a function at a particular place and then use that to write the equation of the tangent line? Why would we ever do that? Well, it's because here's your curve, here's your tangent line. The tangent line's really close to the curve for at least a little while, right? And so what the linearization can offer you, especially in a time before calculators were readily available, it can give you a simple estimation of a very complicated formula. So here's how it works. If f is differentiable at x equals a, then the equation of the tangent line, which although we didn't write it out like this is point slope, right? If you just put a y here instead of an L of x, it's the value of the function at that point. So y plus the derivative, the slope, times x minus a. This is part of why I like point slope, and it's part of why I like point slope in this order, is that it leads you to this equation, and much later on, we will do things where we won't just do linear approximations, but we'll do quadratic approximations, and going on from there, and actually to the place where we come up with what's called an infinite polynomial that we can use to get any degree of accuracy we want. So this is called the linearization of f at a. Now, f of x is approximately equal to L of x, right? As long as we're pretty close to the point in question, we should have a fairly good approximation. The further you get away from the point of tangency, the worse your approximation tends to get. Although, it's certainly possible that eventually, your graph comes back up and they're exactly equal to one another again. So the point x equals a is called the center of the approximation. We're actually going to use that later on for the center of an infinite polynomial. So we're just going to jump into examples. Write an equation for the line. Don't know where the went. Tangent to f of x is equal to the square root of 1 plus x at x equals 0. Then use your equation to estimate the square root of 2. Okay. So f at 0, that doesn't sound good, is 1. F prime of x is going to be 1/2 of 1 plus x to the negative 1/2. So that f prime at 0 is, when I substitute in x is 0, I'm going to get just 1/2. So our linearization, L of x, is equal to 1 plus 1/2 times x minus 0. So if I'm trying to approximate the square root of 2, what does x need to be? This is not it's not a trap. It needs to be 1, right? that's equal to f at 1, which is approximately equal to L of 1, which is 1 plus 1/2 times 1 is 1.5. By the way, in case you don't know, to 3 decimal places, the square root of 2 is 1.414. It's not a terrible approximation. Now, if I was closer, I would get, if I wanted, like, what's the square root of 1.5 or 1.2, this would be a better approximation. Typically, the closer you are to the point of tangency, the better the approximation is. All right, so let's try this one. Find the linearization of f of x is equal to cosine of x at x equals pi over 2, and use it to estimate the cosine of 1.75. Use your calculator to check the accuracy. All right, so f at pi over 2 is cosine at pi over 2, which is 0. F prime of x is negative sine of x, so that f prime at pi over 2 is negative sine at pi over 2. That's negative 1. So my linearization, L of x, is going to be equal to 0 minus 1 times x minus pi over 2. And you can simplify that if you want. That would be negative x plus pi over 2. So cosine of 1.75 is f of 1.75, which will be approximately L of 1.75. So it's going to be negative 1.75 plus pi over 2. Now, if this was on the AP exam, you would just leave it like that, right? You're not going to try and figure out what pi over 2 is and get some decimal approximation for that. But let's check this on our calculator. If we do negative 1.75 plus pi over 2, what did I do? Negative 1.75 plus pi divided by 2. We get negative 1.79 something. So let's try cosine of 1.75. That's a really good approximation. Now, why is it such a really good approximation? Well, part of it is pi over 2 is 1.57, and we're at 1.75. We're really close to our point of tangency. And again, generally speaking, the closer you are to the point of tangency, the better your approximation is going to be. These two I just think are interesting, and you can actually, there are rules of thumb for estimating square roots and cube roots of any number. So let's try this one. Approximating the square root of 123. What's a square root that would be easy to deal with that's close to the square root of 123? Yeah, square root of 121. So for that first one, we're going to let f of x be equal to the square root of x. F of 121 is 11. F prime of x is 1/2 x to the negative 1/2. So f prime of 121 is going to be 1/2 of 1/11. It's 1/22. So the square root of 123 is f of 123, which is approximately equal to L of 123, which would be equal to 11 plus 1/22 times 123 minus 121. Hang on a second. This is what I get for skipping steps. Okay. Yeah. No, something's... Sorry. So L of x should be... we centered it at 121. That's right. So it's 11 and 1/11. And if you put that into a calculator, 11 plus 1/11 is 11.09 repeating. And the square root of 121, or 123, excuse me, is 11.0905. So again, very good, partly because I'm pretty close. We can do the same thing for the cube root. Here, I'll call it g of x is x to the 1/3. Where do I want to center this one? Well, I need a cube root that's close to 123. Yeah. G of 125 is 5, because 5 cubed is 125. G prime of x is 1/3 x to the negative 2/3. So G prime at 125 is going to be equal to 1/3 times 1/10. So that's 1/30. So our L of x, I'll take the time to write this one out this time. I should have done that last time, is 5 plus 1/30 times x minus 125. So the cube root of 123 is going to be equal to G of 123, which is approximately equal to L of 123, because our linearization approximates the value of the function. And that's going to be equal to 5 plus 1 over 30 minus, times 123 minus 125. That'll be a negative 2, so that's negative 1/15, so that'll be 4 and 14/15. Now I want you to notice something here, that this first part got us in the ballpark, right? The 5 did. And this second part got us how much we had to change from that. So this part is sometimes called the differential estimate of change. So if f of x is differentiable at x equals a, the approximate change in the value of f when x changes from a to a plus dx is df, which is equal to f prime of x times dx. So the approximate change in f is the derivative times the change in x. And isn't that exactly what we have here? 1 over 30 is the derivative, and the 123 minus 125 is how much x changed and in which direction. So this part can give you an estimate of the amount of change. So if I look at this problem, suppose that the Earth were a perfect sphere, which it's not, and we determined its radius to be 395 plus or minus 0.1 miles. What effect does the 0.1 mile have on the Earth's surface area? All right, so the area is 4 pi r squared. I started to do the volume. So the change would be the derivative times how much we have changed the x. So dA dr is 8 pi r. So at the point in question, dA dr evaluated at 3959 is 8 times pi times 3959. I'm just going to leave it like that for the time being. So the change in surface area is approximately equal to 8 pi times 3959 times 0.1. So 8 pi times 3959 times 0.1. So that's 8,609.3 or so. And that would be square miles. All right. You guys have a great day. And I will see you Tuesday.